Hi, I'm Professor Seth Chandler at the University of Houston Law Center, and this is a video on confusion matrices, part of course Analytic Methods for Lawyers. Classifiers can produce confusion matrices, which are the counts of all your combinations of actual class, what the truth is, versus the prediction, what you actually classified a case or an instance to be. That matrix, the confusion matrix, is the basis for computing many of the statistics used to examine the performance of the classifier, and it's an indispensable tool of machine learning. It can actually be applied to statistics as well. What I'm going to do in this essay is describe the confusion matrix, many of the statistics you can derive from it, and also a few statistics that we get from the classifier itself and that don't come directly from the confusion matrix. You can think of the confusion matrix as a little bit like a box score in a baseball game or a similar thing in a football or soccer match. It's sort of a master record of what the classifier has found, and you can use it to find all sorts of interesting things. I'm going to focus here on a binary classifier, one where there are only two classes, like true and false, or died and survived. But at the end of the video, in an optional section, I'm going to show you how to use a multi-class classifier with a multi-class confusion matrix. It's not particularly more difficult, but there are a few wrinkles that we need to discuss. I'm going to use a couple of functions in this video that we haven't seen much before in this course. Some of them are sufficiently easy that I really feel comfortable just referring you to the official documentation, and you'll likely be able to intuit how it works without even having to go to it. There are a couple that I'm going to show you as I work my way through the notebook, and there's one that I want to show you now. I use it extensively in that optional section, but I do use it in the main section, and it's not hard. Let's take a look at it. It's called verification test. So here's how it works. Here's your actual output. This will evaluate, and I think it's going to produce 4, and here's what you're expecting to see. So if I run that, I get a very nice thing. It says check. If I did this sort of 1984 style, I would get a bad X. Okay? So the other thing you can do, though, is you'll notice that verification test produces a test results object, and like all other objects, we can sort of ask things about it. And so one thing I might want to do is say, hey, what was the actual output? Instead of having 4, I might have 5 minus 1 as the expected output, and so maybe I couldn't compute that in my head, so I want to see what the expected output is, and then I want to see whether the test was successful, that is, whether the two values were the same. So here you see an association in which we see the actual output, the 2 plus 2, the expected output, the 5 minus 1, and whether they're the same, which it turns out that they are. Okay? If they are not the same, here's what I'm going to see. I'm going to see a difference, and the outcome is going to be a failure. So that's verification test, and we'll look at it on a couple of occasions in this notebook, and I thought I might just warm us up by looking at it now. We'll start with a very familiar data set. It's the Titanic data set, and we're going to build a classifier that tries to determine whether someone's going to live or die based on their age, gender, and cabin class. To do this, we will load up the training data, we will load up the test data, we'll create a classifier function based on the training data, and then we'll produce a classifier measurements object based on the classifier and the test data. So if we run this, we're done, and we have a classifier measurements object, and actually you can see the built-in short form representation of the classifier measurements object actually contains a confusion matrix in it. So what do we see? We see that there are 208 people who in fact died, and the classifier said they were going to die. We get 35 people who in fact died, but the classifier thought they would survive. There are 50 people who survived that the classifier thought would die, and there are 100 people who survived, but the the classifier thought that they would survive. You should be aware there are two equally used conventions about confusion matrices relating to what goes on the rows and what goes on the columns. Wolfram takes the view, as many do, that you put reality on the rows. The actual class goes on the rows and the predicted class goes on the columns. But there are a number of software programs that do it differently and that put the prediction on the rows and the actual class in the columns. There's no right answer. The crucial thing is when you look at a confusion matrix, you've got to figure out which convention they are following. Otherwise, your computation of statistics is likely to be wrong, and you're not going to really understand what's going on. So just be aware that there are two different conventions in use here, and Wolfram is reality on the rows. There are a number of ways of representing confusion matrices. One you just saw, it's that plot, but also you could just get the numbers, and here's the confusion matrix itself. You'll notice that there's this last column of zeros. This is here in case you've asked the classifier to say, in close cases, tell me it's indeterminate. I haven't done that. It's not something I typically do, but that's what that last column is going to be. You could ask to see the confusion matrix in matrix form. So we'll say take this output. That's, remember what percent does. And we'll say matrix form that. And so now it's in a nice, pretty matrix. As I mentioned, the last column are those indeterminates. There are no indeterminate people. That is, you either lived or you died on the Titanic, but maybe our predictor, our classifier, just can't figure it out. The other thing is, if you do want to see the confusion matrix in the form where reality goes in the columns, you can just use the transpose function, which flips rows and columns in a matrix. And then also, if I want, I could represent that in matrix form. And really, this is a little bit cleaner syntax here. Let's do that. All right, so there it is in reality in the columns form. Finally, you might want a prettier version, kind of like we saw up here, but bigger. And if you want that, you can just say confusion matrix plot. The virtue of confusion matrix plot is everything's nice and labeled. If you hover over things, you get tool tips that give you some information. So oftentimes a confusion matrix plot is a useful thing to have. Also, you might want it as a function. That is, you might want a function that you can then apply to things. So let's do the confusion function property of the classifier measurements object, which we've assigned to CMO in this notebook. And there it is, and you can see that it's actually an association of associations in which the outer key represents reality and the inner key represents the guess. Once it is represented as a function, you can then extract information out. Like if I wanted this number 35 here, I could say, okay, get me people who really died, but we predict they survived. That's the function notation. Or I could treat this as a data structure and say, first get me the died part of this, and then get me the survived part of what's left. So either notation will work, and they both give you 35. Finally, you could think of the confusion matrix as creating a joint distribution of reality and prediction. And so we can ask for the confusion distribution of the classifier measurements object. And we get our friend the categorical distribution, in which we have the row categories of died and survived, that's reality, and the guess categories of died, survived, or indeterminate. Now we can do everything you can do with a categorical distribution. By the way, you have lost a piece of information here, which is you don't know how many people were originally in the data set, so just be aware of that. You've turned it into a probability distribution, so we don't know how many people were there. But We can do things like compute the marginal distribution, the first marginal distribution of this categorical distribution, or we can ask to extract the probability array. So those are various things that you can do once you have it as a distribution. We might want to know how many people are in each cell of, or wines or passengers, whatever it is. How many are in each cell of our confusion matrix? And one way to do that is to ask for things like the true negative number. Now, what does true negative mean? Negative, this second part of the phrase true negative, refers to how you classified it. This is what you said it was going to be. True refers to whether that guess is correct or not. So here we're looking at those that we classified as negative and we got it right. Now, for all of what I'm about to show you, for an awful lot of these statistics, negative and positive are sort of arbitrary, right? It could be that survived is the positive category, or it could be that died is the positive category. It kind of depends what I'm interested in. And so, if you don't tell Wolfram language which class you intend to be positive, it will generously give you the answer for both. So if you think that died is the positive category, let's look at our distribution again. Let's just go up here. If you think that died is the positive category, then there were 100 that were negative that you got correct. Okay? Whereas if you think survived is the positive category, then there are 208 that are negative, they died, and that you got correct. So for all of these statistics, you need to realize that it depends on the positive class. Some statistics programs are a little less rigorous about this, and they'll kind of make assumptions about what the positive class is. Wolfram language does not, and I actually think that's a better convention. It'll give you answers for both, or if you want to pre-specify something as the positive class, you just use this notation. You say, give me the true negative number under the assumption that survived is the positive class, and it's going to tell you that's 208. Okay, so we have the true negative number, false positive number. False positive are people that you thought would be positive, but you were wrong. So in our case, if we were to designate survived as the positive class, then there would be 35 people that we thought were positive, but we were wrong. They are in fact negative because they died. Okay? So that is the false positive number. The false negative number are people who who we said were in the negative class, and we were wrong about that, actually. They were a member of the positive class. And so if died is the positive class, then there are 35 cases in which the person actually died, but the classifier said they would survive. And if survive is the positive class, there are 50 people in which the person actually survived, but the classifier said they would die. So there we go. That's the false negative number. The true positive number is, we've designated a positive class, and now we want to know of people, how many people that we said were positive were in fact positive. That's the true positive number. Okay? And here, if died is the positive class, then we have 208 people that we said would be members of the positive class and in fact did die. Whereas if we said survived was the positive class, there would be 100 people that we said would survive, and we got it right. Okay, so for each of these basic number categories, there's a corresponding rate category. The number values that we just computed are going to be the numerator of a fraction, and I now need to talk about, well, what's the denominator that we use in computing the rate. So let's look at the true negative rate. This is the fraction of times your classifier said a case, a passenger, a wine bottle, was not a member of the positive class, and in fact, the case was not a member of the positive class. The classifier got it right. So, if survived is the positive class, then there are 208 instances in which the classifier got it right, and there are 243 instances, 208 plus 35, when in fact the person was negative. They didn't survive. So that's how we could sort of compute it by hand, or we could ask for the true negative rate property of the classifier measurements object. And there we go. Okay, now you might find it annoying that we keep getting two answers, that it keeps depending on which class we say is the positive class. One way is just to live with this issue and designate a positive class. But there is an alternative way that's sometimes used, and that's to use some form of averaging. And there are at least 3 forms of averaging that you can use. I'm going to give you the simplest one first, although unfortunately it's not a particularly good measure. But the idea is you just take the average, okay? That's how you compute the true negative rate of the classifier without thinking through what's the positive class. So to do this, one way to do it is to say, give me the true negative rate, and I want the macro average. Here I'm going to compute it by hand. I'm going to get the true negative rate. This gives me both values. Value strips out the keys, and mean finds the mean of that value, and hopefully this will all come out the same, and hooray, it does. Okay, there are 2 better ways to do it. Unfortunately, if you do it by hand, it does require a little bit of computation. The idea is to weight these values according to how many people are in each category. So there are 243 people who died, so let's weight the true negative rate for the died class to be 243 393rds of the total, since there are 393 passengers in the test data, and we'll weight the survive by 150 because there are 150 people who survived. So this is how you would do it by hand, as it were. Or you could, instead of asking for the macro average, you could ask for the weighted macro average. And I think that's a better way of doing it. Here the result is slightly different, maybe not hugely, but at least you'd be doing it correctly. Finally, you can use something called the micro average, which I think is somewhat of a nuisance. You basically take the numerator of both statistics and add that up, and that's the new numerator. And then you take the denominator of both statistics and you add that up, and you make that the denominator of the final fraction, and then you compute the fraction value. Or you could just ask Mr. Wolfram to do this for you by asking for the micro average. So that's how you can, one way of addressing this distressing to some situation in which you get different values for these rates depending on which class you designate as positive. All right, and so what I just told you about weighted macro average and all that stuff, that's true for all of these statistics that follow. I'm not going to say this again every time we do a statistic. All right, the false positive rate. This is the fraction of times your classifier said a case was a member of the positive class, but you got it wrong. It's not a member of the positive class. And so if died is the positive class, the numerator is 50, because there are 50 instances in which the classifier falsely said that the passenger died, and the denominator, is all the times when the passenger did not die. That's 150. So the fraction is 50 over 150, which is 0.333. Or if you find this hard to do, you can just say, hey, classifier measurements object, would you please tell me the false positive rate? And it will. Okay. In everything I've done up to now, our denominator has been computed through row sums. That is, I'm looking at the denominator is always how many people are actually either in a class, in the case of a positive thing, or not in a class, in the case of a negative thing. I now want to flip that for the next two statistics, and now our denominator is going to be prediction oriented. So the positive predictive value is often exactly what you want to know about a classifier. It's how likely is it that you really are positive if the classifier came back positive. The numerator is the true positive number, but the denominator is the sum of everyone classified as positive. So if survive were the positive class, the positive predictive value is 100. That's the number of true positives. The denominator is everyone we classified as positive, which is the 35 who actually died and the 100 who lived. And so that fraction is 0.74. And so we need to change that number. That's an old number from a previous thing. Again, we can just compute this directly, and we can see that it's survived as the positive class. The positive predictive value was 0.740. And so, if supposing you were you were on the Titanic and you had your classifier somehow, and the iceberg has hit the ship, and you say, how are things looking? And the classifier says survived. Well, you would feel that that meant that your chances of actually surviving were 0.740741. So I don't know what you would do with that information, but you could compute it. All right, the negative predictive value, it's the same idea. We're going to have a column-focused denominator. The numerator is how many true negatives there are. So if survived is the positive class, then the number of true negatives is 208. And the denominator is everyone that we predicted would be negative. So that's the 208 that we got right, and the 50 that we got wrong. So the denominator is 258. The fraction is 0.806202. And again, if you were on board with your very advanced machine learning system on the Titanic, and the classifier says died, then you know your probability of death would have been about 0.805, and that would be very sad. All right, but rather than this whole story, we could just ask Mr. Wolfram to compute it directly, and there we go. So if survived is the positive class, then the negative predictive value is 0.806. I think I told you at the outset of this video that there were a few statistics, properties of classifiers that you couldn't quite get out of the confusion matrix, and I'm about to go through a couple of them. These are ones that look at how the classifier behaves with respect to each person or line or whatever it is that it confronts. And so if I say CMO probabilities, if I ask for the probabilities property of the classifier measurements object, I get the probability that the classifier got it right, got the actual class in each case. That is, remember what the classifier is doing is it's really coming up with a probability distribution over classes. Often you don't see that. You just want to know what's the most likely outcome. You don't need to know that, well, there's a 37% chance it's something else. But when you ask for probabilities, it's actually going to do that. It's going to figure out probabilities, and it's going to give you the probability that's associated with the correct class each time. So that's the probabilities property. It's the probability of the classifier getting the actual class in each case. And as you can see, there are 393 values because there were 393 passengers in the test set. So one thing you could also do is make a histogram of those probabilities. So to do that, you use the probability histogram property. And ideally, you'd like everything to be a 1. That is, it was very confident of its answer every time it got it right. So these are instances here, for example, where it got it right probably, but it wasn't very confident. And here, where we're getting probabilities of 0.3 and 0.2, it's actually making the wrong decision. You can see there aren't too many instances where it really was confident of something and it got it wrong. So we'll come back to probabilities in a moment when we look at cross entropy and other exciting things. Okay, back to our confusion matrix statistics. Accuracy. This is often what you want to know most about a classifier. How accurate was it? So there's a very simple measure, which is how often, what fraction of the time did it get the right answer? And you can just read that right off the diagonal of the confusion matrix. So it got it right 208 times, died, 100 times, survived. So that's 308. And the denominator is everybody in the matrix, so we know that's 393. And so that's our accuracy value. Or if you find that too tedious, you can just ask for the accuracy property of the classifier measurements object, and you get the same number. It's often useful to know how accurate your classifier would have been if it just guessed the modal class. That is the most common thing. And here, the most common thing is for people to die. So if you just said everybody dies, like Dr. House does on his television show, then you would get it right 243 out of 393 times, and your accuracy would be 61.8% of the time. So, one thing you might want to do is to calibrate your sense of how accurate your classifier is by looking at what your baseline accuracy is. Now, this would be a very weird classifier in that it never would guess that someone would survive. But if all you care about is getting the right answer as frequently as possible, then you should just make the modal guess every time. And the accuracy baseline property of a classifier measurements object gets you precisely that. Now it's time to talk about one of my very favorite statistics, the Cohen-Kappa statistic. And let me try this out on you. Supposing you were you assumed that your classifier was worthless. You would still get some correct answers, okay? And so you would get a certain accuracy level just by luck. That might serve as kind of a baseline, and what you'd be interested in is how far between luck and perfection, which would be an accuracy of 1, your accuracy level lies. So we're kind of rescaling the accuracy. Instead of going from 0 to 1, or we're rescaling it to see where in between luck and 1 the classifier falls. So if it falls 40% of the way between luck and 1, your Cohen-Kappa statistic is 0.4. And actually, this is kind of interesting. Like, let's suppose that the Supreme Court reverses 70% of the time it takes a case, and it affirms 30% of the time it takes a case. And you do a very elaborate study of Supreme Court cases, and you find that your classifier is able to get it right. It's accurate 75% of the time. And you start bragging to the world that you've got a great classifier. It gets it right 3/4 of the time. Well, that's true, but it's also true that a random classifier would get it right 58% of the time. That is, there'd be like 49% of the time when you guess reverse and it would reverse, and there'd be another 9% of the time when you'd guess affirm, and in fact the court would affirm. So your classifier is like 40.5% better than luck, which is good. Nothing too embarrassing about that, but it is a little less impressive than that 75% number. The way we compute a Cohen-Kappa is very similar to the way we did computations of chi-square statistics. If you hearken back to that, we're going to take the marginal distribution of the categorical distribution representation of the confusion matrix, and we're going to take first on the first marginal, then the second marginal, and we're going to take the product distribution. So this is what the distribution of actuality and guess would look like for a worthless classifier, and we'll call that PD. We're then going to compute the PDF of our worthless classifier for the times that we would still get it right as a result of guessing. Died, died, survived, survived. And we'd add that up. And that would be our luck value. That's how accurate we would be just as a matter of luck. And now what we simply do is to rescale our computed accuracy to see how far between luck and 1 it lies. And you can look up the rescale command if you want to see exactly how it works. So if we do that, we get 0.53283, which is, well, that's not bad. And then let's see, just make sure what Mr. Wolfram thinks the Cohen-Kappa property is of our classifier measurements object. And thank goodness, after all that discussion, it's the same. Now it's time to talk about one of my very favorite statistics, the Cohen-Kappa statistic. And let me try this out on you. Supposing you were you assumed that your classifier was worthless. You would still get some correct answers, okay? And so you would get a certain accuracy level just by luck. That might serve as kind of a baseline, and what you'd be interested in is how far between luck and perfection, which would be an accuracy of 1, your accuracy level lies. So we're kind of rescaling the accuracy. Instead of going from 0 to 1, or we're rescaling it to see where in between luck and 1 the classifier falls. So if it falls 40% of the way between luck and 1, your Cohen-Kappa statistic is 0.4. And actually this is kind of interesting. Like, let's suppose that the Supreme Court reverses 70% of the time it takes a case, and it affirms 30% of the time it takes a case. And you do a very elaborate study of Supreme Court cases, and you find that your classifier is able to get it right. It's accurate 75% of the time. And you start bragging to the world that you've got a great classifier. It gets it right 3/4 of the time. Well, that's true, but it's also true that a random classifier would get it right 58% of the time. That is, there'd be like 49% of the time when you guess reverse and it would reverse, and there'd be another 9% of the time when you'd guess affirm, and in fact the court would affirm. So your classifier is like 40.5% better than luck, which is good, nothing too embarrassing about that, but it is a little less impressive than that 75% number. The way we compute a Cohen-Kappa is very similar to the way we did computations of chi-square statistics. If you hearken back to that, we're going to take the marginal distribution of the categorical distribution representation of the confusion matrix, and we're going to take first on the first marginal, then the second marginal, and we're going to take the product distribution. So this is what the distribution of actuality and guess would look like for a worthless classifier, and we'll call that PD. We're then going to compute the PDF of our worthless classifier for the times that we would still get it right as a result of guessing. Died, died, survived, survived. And we'd add that up. And that would be our luck value. That's how accurate we would be just as a matter of luck. And now what we simply do is to rescale our computed accuracy to see how far between luck and 1 it lies. And you can look up the rescale command if you want to see exactly how it works. So if we do that, we get 0.53283, which is, well, That's not bad. And then let's see, just make sure what Mr. Wolfram thinks the Cohen-Kappa property is of our classifier measurements object. And thank goodness, after all that discussion, it's the same. Let's go to another cage in our confusion matrix zoo, or another pavilion. And these are some special accuracy measures. What's tricky about these is not so much the concept, but that different people use different names for exactly the same thing, and which name you use depends on which discipline you're in. So one of these is sensitivity, or sometimes called recall. It's exactly the same thing as the true positive rate. So it's saying, given that a person really is positive, what fraction of the time will the classifier say so? And you can ask for that property simply by putting in sensitivity. You could also put in true positive rate, or you could put in recall, and you get exactly the same thing. Specificity. Specificity is exactly the same thing as the true negative rate. How frequently does the classifier guess negative when the person really is negative? So there we go, and we can see that the specificity is exactly the same as the true negative rate. Then there's precision, and the only way I can remember this is pre is the same thing as predictive. So if that helps you as a mnemonic, good. If not, you're just going to have to memorize it. But precision is the same thing as positive predictive value. It's kind of a Bayesian statistic, just like positive predictive value is. I sort of went through that Bayesian story before. You can just ask Mr. Wolfram for the precision, and you can see that the positive predictive value is exactly the same thing as the precision. All right, you didn't think we were going to get through this video without a discussion of entropy. There are a number of entropy measures you can have on a classifier, and they're very useful in comparing the performance of different potential classifiers on the same data. And unlike most of the measures I've already discussed, they thankfully do not depend on the somewhat arbitrary designation of one of the classes as a positive class. So let's look at the first such entropy measure, and this is the mean cross entropy. Okay, so we have reality, that is, there's a 100% probability that the person died and a 0% probability that the person survived. Let's assume that we know to a certainty what actually happened in each case. That's our target distribution. That's what we'd like our classifier to get to. And we have, as I've mentioned, a probability that the classifier is output. I think there's a 37% chance the person died and a 63% chance the person survived. So those comparisons, as you remember from our cross entropy video, let you compute, in a sense, the difference between our actuality and our guess. So what we want to do is then to take each person, each passenger in our test set, and compute the cross entropy for them, and then to take the average of that. And that will be some measure of how good our classifier is. If the classifier is perfect, we're going to see a mean cross entropy of 0. If it's less than perfect, we're going to see a higher cross entropy. And so I'm running through here the code of how you actually compute it. I think rather than walk you through it, I'll let you sort of read your way through this code. The idea is you start with the examples. To get the actuality, you want the last value. Remember how each example fed into a machine learning algorithm tends to be a rule, and the left-hand side of the rule are the features of the individual, and the right-hand side is the correct answer. So we want the correct answer. If it's survived, we'll represent that as 0, 1. If it's died, we'll represent that as 1, 0. So that's going to give us the actual probability distributions, with each person represented as 2 numbers, depending on whether they survived or they died. And then we'll take the same examples. We'll get the left-hand side this time, And then we will say, hey, what does our classifier function think the probabilities were? That's going to give us an association. We just want the values, and those values will be the predicted probability distributions. So this is going to, I'll just run this here. This is going to give us our actual probability distributions. This is going to give us our classifiers distributions. And you remember the formula for cross entropy. It's the expected value of the log of the predicted distribution subject to the actual distribution. And you can compute that as the dot product of P, the actual distribution, with the log of Q, the predicted distribution, and then you have to take the negative of it. So that's what this code here is doing. And at the end of all of this, we're just going to take the mean. So if anyone ever made you do it by hand, which would be kind of mean, you could do it. Or, thankfully, you don't ever have to see this again. You can just say, hey, Wolfram kernel, what's the mean cross entropy? And it would tell you. Okay. There's perplexity. Perplexity, remember, it's like it's the equivalent of a die throw. How many faces does a die have to represent the uncertainty of our situation? So we could compute that as the exponential of the mean cross entropy, and it's 1.61. So we've sort of got, after we're done with our classifier, we're left with a situation which is kind of like a die with 1.61 faces, if that helps you. And you can see that you never have to do this again. You can just say, hey, give me the perplexity property. All right, there's also the class mean cross entropy. And this is not really conceptually any harder. It's saying, hey, what's the cross entropy for people in each class? You only want to look at the people, for example, who survived. What's their mean cross entropy? And then you want to look perhaps at only the people who died and ask what's their mean cross entropy. So the code here is very, very similar to the last code. The only thing I've had to do is use a function called pick. And let me see if we haven't used much picking before, so let me show you pick. So it has 3 arguments. First argument, second argument, third argument. It says pick from the first argument only those members where the corresponding member of the second argument satisfies the pattern in the third argument. So for 1, we look at 2, and we say, is 2 odd? It's not, so we don't pick 1. 35, we look at 4. Is 4 odd? No, it's not. So we don't pick 35. 3, we look at 5. Is 5 odd? Why, yes, it is. So 3 gets picked. And we go through this for each one of these and looking at the corresponding element in the second argument, and we then see if it matches the pattern. So we end up with 3, 10, and 24. Notice we're not asking whether these numbers are odd. We're asking whether their corresponding values in the second argument are odd. And so that's what I'm doing here. I'm only taking those actual probability distributions where the person actually died, and then for the predictions, I'm only taking the predicted probability distributions where the person actually died, and then I'm doing the cross entropy thing and taking the mean. I do the same thing here. The only thing different in this code is I use survived, and thankfully, again, you never have to see this again. You can just ask. But I think it's important to understand what the concept is. That's why I run you through the code, so it's not just a black box, but so that you can appreciate what's actually being computed. Time to learn about a really important concept in classification and in confusion matrices, the ROC curve. ROC stands for Receiver Operating Characteristic, and it originally comes out of signal processing, but it actually is very useful here. Let's talk about what the ROC curve is. Oh, by the way, it's also going to prove to be crucial to our understanding about issues of discrimination in looking at classifiers. Okay, the idea. Our classifier actually has a utility function that's sort of working behind the scenes when it tries to guess what each passenger is. There was one that was used to build the Titanic classifier. I'm going to show you what it is here. I'm going to say, hey, get me the classifier function that you used and tell me what utility function you used. I'm not interested in what it did with indeterminate cases because we don't do indeterminate in this class. So let's get that. All right, there it is. So here's what it's telling us. It's the outer key here is what actually happened, and the inner key is what you guessed. So if what actually happened was the person died, and I correctly guessed that they died, I get a point. If they actually died and I said they survived, I get no points. And if they actually survived and I said they died, I get no points. But if they actually survived and I said that they survived, I get a point. So this may seem very obvious, but we're going to actually change this later on, and you'll see what happens when we change this. One little complexity here is in order to make this code work, I have to rewrite this function and just tell it that reality and the guess are strings, like died is a string and survived is a string. So don't get too worked up about that, but that's what UFS is. All right, so now, supposing the classifier says, I think there's a 1 minus p probability that the person dies and a p probability that the person survived. And 1 minus p plus p equals 1, because in our model, in our world, either they survived or they died. So supposing I guess that they died, what's my expected utility if I make that guess? And so the way we're going to compute that is we realize we have a categorical distribution here over died and survived with probabilities 1 minus p and p. And we're now going to find what's our expected utility for that guess. And I'll take the expectation. So that's our died expected utility. And then we can compute, hey, what's the expected utility if we guess that they survived? And so here we're going to say, here's our categorical distribution. And now what we're interested in is what's the expected utility if they survived given that guess. So we compute that. So we now have our expected score if in fact they died, and if we predict they died. Our expected score if we predict they died. And here's our expected score if we predict that they survived. And now I want to find out which guess is likely to give us a higher utility. So I'll use reduce for that, and I'll add a quiet because it comes up with an irritating warning. And it tells me, okay, if p is less than 0.5, if the probability that they survived is less than 0.5, you should guess that they died. And if the probability is greater than 0.5 that they survived, you should guess that they survived. And you very well might be thinking, my goodness, Professor Chandler, that's an awful lot of work for something that's obvious. You just pick the most probable outcome. And that's true, but what if the costs of error are not symmetric? Or what if we get more points for correctly predicting someone will die than correctly predicting that they will survive? Maybe we'd make a different decision. So let's use a new utility function. Here it is. I'm going to say it's worth 4 times. To correctly guess that they died is worth 4 times as much as correctly predicting that they survived. Now I'm going to do exactly the same computation that I did before. I'm just going to compress it into one line so I don't have to write it all out, and find out for what values of p will we be better off predicting that they died. And now it turns out I should predict that they died if the probability of them surviving is anywhere between 0 and 0.8. So that's very important. This means that our utility function helps determine the classifier's decision. And it sets this threshold value, 0.8 here, which is associated with 4, and 0.5 here, which is associated with 1. Okay? So what this means is that since our utility function determines our decisions, and our decisions affect the confusion matrix, As we increase the relative value of guessing death correctly, the fraction of people we predict will survive declines. Maybe you could have thought of that without all this math rigmarole, but it's not so obvious. And what this means in terms of the confusion matrix, which I'm going to put back up here, is that as we increase the relative value of guessing death correctly, people can't migrate from death to survive. That is, our classifier cannot affect the real world. It can just affect our classification. And we're going to see people start to move from the right-hand survival column to the left-hand death column. Let's check this point. So I'm going to run this code, and we're going to compute the classifier measurements using our classifier, using the test data. We're going to produce a confusion matrix plot, but our utility function is going to be a function actually itself of D, which is that relative value of getting death correct. And I'll let that vary from 2 to the negative third, 1/8, to 2 to the third, 8. And so let's see what happens to our confusion matrix as we change the utilities from different forms of guesses. And here we are. So you can see that when guessing death correctly is only worth 1/8 as much as correcting survival correctly, we're sort of leaning heavily on survival. But now as we start to increase the value of getting death right, we're starting to see migration, at least here, from the survival category to the death category. And as we keep increasing and increasing, by the time we're up to 8, we're barely predicting that anybody survive, because we get so much value from predicting deaths correctly that if we lose a few survives correctly, it's not such a big deal. This is the idea behind the ROC plot, that by changing the decision utilities, I'm basically changing a cutoff value, a threshold value, and as I do that, my confusion matrix morphs, and as my confusion matrix morphs, all the statistics that depend on the confusion matrix change. So what statistic does the ROC curve want to look at? It wants to look at 2 specific statistics, the false positive rate and the true positive rate. So this is essentially the same code where I'm basically letting the relative value of getting death correctly vary. I'm going to let it vary this time over a bigger range from 2 to the negative 8th, 1/256th, to 2 to the 8th, 256. And I'm going to assume that survived is the positive category, and I'm going to get for each of those weights the false positive rate and the true positive rate. Chunk, it did it. And now what I can do is I've got a bunch of points, and now I can plot them. So don't worry about this code. This is just to plot it and label it. And see this curve? It goes from 0, 0 all the way up to 1, 1. That curve is the receiver operating curve. Okay? Now, there are much more efficient ways of computing the receiver operating curve than I just used. I did it in a fashion that I thought was pedagogically useful. The Wolfram kernel does it in an efficient way, and so it gets lots of points. And so if we want to see the ROC curve for a classifier, we can just ask for the ROC curve property, and we can designate, if we choose to do so, the positive class. And if I do that, that's the picture I get, which does basically look like this picture here. What's this shaded business? And what's this legend? Okay, so here's my ROC curve. Here's what the ROC curve would look like for basically a worthless classifier. The false positive rate would be equal to the true positive rate, which it unfortunately labels as recall, because it wouldn't be able to tell who's positive and who's negative. So the area between, this shaded area between the ROC curve for the classifier we have And the ROC curve for a worthless classifier has a name. It's called the AUC, the area under the ROC. The concept, by the way, is very, very similar to the Cohen-Kappa statistic, where you're sort of calibrating the worth of the statistic by reference to what a worthless classifier would do. The Wolfram language, the classifier measurements object, has this AUC property. It calls it area under ROC curve. And again, you can designate the positive class. It's 0.827. Or if you want to do this whole exercise using DIDE as the positive class, you get the same area under the ROC curve. That's right, the area under the ROC curve stays the same. Last topic before we get to the optional stuff for multi-class classification, and that is calibration. So, if a classifier is properly calibrated, then among those passengers that it says, hey, you're 10% likely to survive, well, really about 10% of them should survive. It shouldn't be that if it says 10% are likely to survive and we look at that group, that 40% of them survive. It might be making the right decision, but the probabilities aren't calibrated correctly. There's a mismatch between the probability output of the classifier and reality. And so we might in that circumstance want to recalibrate the probabilities that have been output. Let's look at how our Titanic classifier is calibrated. I'm going to produce the graphic here. I'm not going to derive this. So the property is calibration curve, and we get this picture. And actually, that's a pretty well-calibrated classifier. Very nice. Because the blue line, the blue heavy line is right over just about the dashed perfect calibration line. So what this is saying is that the predicted probability, which is on the x-axis, matches the actual probability very well. Now, you'll notice that the line is derived actually from these vertical lines. There is some uncertainty in all of this, and that's what these bars are trying to tell us. But really, that's a very nice calibration, and Wolfram does try to calibrate its outputs, at least as of version 12.2, which is that you're using. If you start to see values where the blue line is off the dashed line, then the classifier isn't calibrated correctly, and you may need to do some additional work if what you're concerned about are probabilities. You'll also notice the scale here is kind of weird. There's a lot of emphasis on small values and very big values, and not so much emphasis on values in between. If you want to see it with a more conventional scaling, you can ask for a linear calibration curve, and now it's a typical linear scaling. But the classifier, it's the same calibration curve, it's just presented in a different way. Okay, that is everything you would ever want to know about classifiers and confusion matrices for binary classifiers. What I'm now going to do in the optional segment is talk about the tweaks you have to make to adapt this to multi-class scenarios. And basically the trick in most cases is to turn the multi-class scenario into a binary classification and then use everything that you already know. But for those of you who are done, thanks for your attention. You now know one heck of a lot about classifiers and confusion matrices, and hopefully you are not confused. In this optional part of the video, I want to talk about multi-class classifiers and how you get statistics out of them and understand their performance. Okay? So I need different data because the Titanic is binary. I'm going to use the wine data. Now the wine data you may recall from prior videos, it gets values I think between 3 and 9 for wine quality. I don't want to have 7 different, whatever that is, classes. Let's just go with 3, and so I want to lump some of the wine categories together. So I'm going to say that any wine that has a rating of 7 or more is good, any wine that has a rating of 5 or less is bad, and otherwise it's a fair wine. So I'm going to suck in the training data, the test data, I'm going to do some reclassifying, and I end up with what I'll call wine training and wine test. All right, so we're done. Now what I want to do is, you now should be very used to this. I want to create a classifier function. I want to create a classifier measurements object using our multi-class classifier CLM on the test data. And then let's take a look at our friend, the confusion matrix. Right, we're done. And there is our wine classifier, where we can see the actual class of the wine on the rows and the predicted class of the wine on the columns. Let's talk about positive versus all reduction of multi-class confusion matrices, a topic that just should make your heart go pity-pat. All right, let's look at the confusion matrix here, and I'll call that M, and I'll present it in matrix form. I think it's easier to say that. Now, suppose we want to designate fair as the positive class. Remember, fair is the middle thing here. So what I then want to do is I want to total up every number that's not fair, like those numbers and those numbers and those numbers and those numbers, and actually those numbers too, and add all those numbers up. And that's my negative numbers, because those wines are not fair, and they're not classified, or they're not classified as fair. And my positive class is just going to be basically these numbers, or positive things are going to be these numbers and these numbers. So I'm going to take basically our 3x4 matrix, although it's really sort of a 3x3 matrix, since these last 0 columns are that irksome indeterminate thing I discussed in the main section of the video, and turn it into a 2x2 matrix. And once it's a 2x2 matrix, then I know just what to do. I just do what I did last time with my 2x2 confusion matrix. To do this, the code relies on a function delete that we haven't seen much of. Delete's real easy. Here I have these letters of the alphabet. This says delete the 4th letter of the alphabet, so I delete D, and I get A, B, C, E, F. And I'm going to use transpose. Transpose says take a matrix and flip it on its side, or to be more technical, reverse the roles of rows and columns. So here is our matrix flipped on its side. Now, with delete and transpose under our belts, I can show you the code for how to compute positive versus all, which is going to take a matrix, a confusion matrix. It's going to take a designation of a class as positive, which is going to be a number, like fair would be the second. I would use 2 because it's the second class in the listing here. And then what it's going to do is it has this function which says add up everything that's not in the positive class, and then just get what's in the positive class and make a list out of that. And what I'm going to do is I'm going to reduce the confusion matrix according to that function f along the first axis. I'm going to flip it on its side, and then I'm going to do the exact same thing, but this time on the second axis. And you can play with that and see how it works, or you can just trust me that it works. And now I'm going to run positive versus all on our confusion matrix. The 2 means I'm using fair because fair is the second class. That I'll assign that to M2, and I'll present it in matrix form. So there is the positive versus all reduction of the original confusion matrix. And when all is said and done, under the way I've coded this, the positive class is always in the second row, the positive guess is always in the second column, and the constructed negative class is always in the first row or the first column. So now we can just use this just as we did before and get all those number values that we got before. So here I'm going to take and I'm going to compute the true negative number under the assumption that fair is the positive class, the false positive, the false negative, the true positive, using our big fat 3x3 confusion matrix. And if all goes well, this value should be 391, and this value should be 254, and this value should be 294, and this value should be 359. I sure hope that works. And hooray, it does. So we could also compute the true positive rate now, just as we did before. So the true positive rate is, that's not right. Let's fix that, and I'll come back and fix this video. I'm back. All right, so what just happened there? Why were the numbers wrong? The reason the numbers are wrong was I forgot something, which is that my classifier that it used was a random forest, and random forests are random. And so you can get different answers each time. They won't usually be hugely different, but they can be slightly different. And that's why the numbers I was getting when I wrote this notebook are different than the numbers I'm getting when I'm executing it today. Anyway, I think I have resolved that problem. And so now these numbers should, I think, all match up. All right, so the true positive rate is this 359 number. That's the number of true positives. And how many positives are there? There are 359 plus 294. And let's just do this by hand and make really sure that I'm getting this right, because if I give you the wrong information, then you're going to get confused. And yes, all right, it's now fixed. Okay, so that's computing the true positive rate by hand. Let's run our verification test. Here I'm going to take that matrix here and get computed by hand. And then I'm going to compare that to what Mr. Wolfram thinks the true positive rate is using the unreduced confusion matrix on the assumption that the positive class is fair. And when we do that, we have success. Hooray. You can compute the other special accuracy measures using this reduced matrix. Here I'm going to show you what specificity is. Remember, this is the true negatives divided by all of the negatives. And so I'm going to compute it here using the reduced confusion matrix. And here I'll compute it using the specificity property of the unreduced confusion matrix, designating the positive class as fair. And hooray, they come out the same. Okay, entropy measures are the same for multi-class classifiers as they are for regular classifiers. You can read why that is here. ROC curve. ROC curve is, we do use a reduced we use a reduced confusion matrix and a reduced classifier. That is, when we designate something as the positive class, we then say, well, everything else is negative. And so basically what we're doing in the ROC curve is to change the weight given to a correct answer for the positive class and see how that alters the true positive rate and the false positive rate as we derive it from the reduced confusion matrix. So I'm not going to go through that by hand. That's a little tedious. I'm just going to show you what it looks like. And here is the ROC curve for our wine classifier when the positive class is fair. And you can see that it's not doing that great. This area under the curve is not so big. And frankly, I think this is because a lot of wine classification is nonsense. And therefore, the sort of answer that is the right answer is sort of this mixture of, yeah, it has something to do with the wine, and then it has something to do with the mood of the taster on that day. There are two measures where we can't use the reduced confusion matrix. We have to use the whole big thing. One is baseline accuracy, because we need to figure out what fraction of wines are actually in the most popular wine class. And here those are fair wines. And so if we don't know anything about a wine, we should guess that it's average, it's fair. Okay, so we can compute that by hand. That's 653, which is the number of fair wines divided by all the wines. That's how accurate we would be if we just said everything is fair. Or we can ask Mr. Wolfram to compute the accuracy baseline statistic, and we can verify that those are thankfully the same. Cohen-Kappa. Cohen-Kappa, you can't do the reduced matrix. Instead, you have to construct the distribution of reality and guess. If the two were completely independent of each other, That will let you calculate how many you would get right by luck, and then you recalibrate your accuracy by seeing what you would obtain by luck. So we can do this. We're going to get the confusion distribution of our classifier, call that CD capital M, and this is the same code I had before. We're going to take the two marginals, and we're going to find the product distribution, which assumes that they are independent of each other. And then what is luck? Luck is the total probability of us getting it right, which means it's actually bad and we guessed bad, it's actually fair and we guessed fair, it's actually good and we guessed good. Add that up, and then use that luck value to rescale our accuracy. So that is our Cohen kappa. I guess I shouldn't have a semicolon there. Let's see what it is. 0.293. So it's remember, this is not a good classifier as our Titanic classifier for the reasons I think I discussed about wine evaluation. And we can verify that our hand-constructed Cohen kappa is the same as the Cohen kappa statistic that the Wolfram kernel computes from the unreduced confusion matrix, and blissfully they are. So those are the adjustments you need to make when you're dealing with a multi-class classifier. Most of the time you just use positive versus all to reduce it to a 2x2, and then use everything you've learned. Occasionally you're going to have to actually do these computations here, but in all these cases, if you just remember what the property is and you have access to Wolfram language, then you can just ask it for the property based on the unreduced classifier. Thanks for your rapt attention.